A small, incredibly cheap AI model just beat OpenAI's massive flagship model in a battery of complex logical tests.
Yeah, and the most fascinating part is that it didn't do it by suddenly growing a massive neural network, or consuming more power.
Right. It achieved this simply by writing its own custom Python script to forcefully stop itself from doing incredibly stupid things.
Exactly.
So imagine for a moment that you decide to hire a world-class architect. I mean, an absolute prodigy.
Okay, I'm picturing it.
This architect can draft the complex blueprints for a state-of-the-art 100-story skyscraper in a matter of seconds.
Wow.
Yeah, they flawlessly understand structural engineering, they can recite the entire history of modern design, and they calculate wind resistance formulas in their head.
Sounds like the perfect hire.
You would think so, but when you finally ask this absolute genius to simply walk through the front door of the building they just designed, they confidently stride forward and smash their face repeatedly into the solid brick wall right next to the open door.
Yeah, which is hilarious, but it really highlights a bizarre disconnect between profound intellectual capability and basic functional navigation.
It really does. And this isn't just a hypothetical limitation.
No, it is the defining bottleneck in artificial intelligence right now. We are dealing with systems that possess brilliant semantic understanding, yet they lack the spatial and physical grounding to operate within rigid environments.
Welcome to today's deep dive. If you've been following the AI space, you know that keeping these systems on track is an expensive, maddening challenge.
It is deeply frustrating for developers, yeah.
Totally. So today, our core mission is figuring out how we can make advanced AI agents build their own guardrails. We are unpacking a rigorously detailed paper from Google DeepMind, published in March of 2026, titled AutoHarness.
It's a brilliant piece of research.
It really is. We are going to look at how a smaller model, Gemini 2.5 Flash, essentially outmaneuvered heavyweights like Gemini 2.5 Pro and GPT 5.2 High.
Just by writing a piece of glue code.
Right, a harness to manage its own behavior. But before we get to the self-writing code, we need to look under the hood at the disease itself.
The root cause.
Exactly. Why do these models trip over their own shoelaces the moment you put them in an interactive environment?
Well, the researchers define this as the action applicability problem.
Action applicability.
Yeah.
Well,
And to put hard numbers to it, they analyzed the Kaggle Game Arena chess competition.
Kaggle is basically a massive proving ground for data science models.
Exactly. It's highly adversarial.
Yeah.
And the telemetry from the Gemini 2.5 Flash model during these chess matches was just staggering.
What did the numbers look like?
78% of its losses were not the result of strategic blunders.
Wait, really? So it wasn't getting outplayed in the endgame?
No, not at all. It wasn't falling for complex traps. 78% of the time, it lost by forfeiture because it simply tried to make an illegal move on the board.
That is insane. More than 3/4 of its failures are essentially disqualifications.
It's exactly like your architect walking into a wall.
Yeah, in the context of a chess tournament, it's like a grandmaster who knows every iteration of the Sicilian defense suddenly deciding they want to move their pawn backward.
Or, try to teleport their rook through a solid wall of other pieces.
Right. It's a total disconnect between high-level conceptual strategy and the rigid physics of the board.
And when we look at the underlying architecture of these models, the reason for this physical clumsiness becomes incredibly clear.
Because of how they're trained.
Exactly. A large language model is fundamentally a next token predictor.
Just guessing the next word.
Right. It generates text by calculating the statistical probability of the next word in a sequence, drawing from a vast multidimensional vector space that was mapped out during its training on internet data.
So it doesn't actually see a chessboard.
No, not at all. It does not possess a 2D array or a visual representation of a wooden chessboard in its localized memory. It has no internal physics engine.
Wow.
It builds its world model based purely on linguistic correlations.
So it's essentially predicting what text characters normally follow each other in a printed transcript of a chess game.
Correct. And because its world model is purely statistical, it is highly susceptible to hallucinating valid state transitions.
State transitions meaning?
Just the process of moving from one legal arrangement of the board to the next. So the AI might accurately calculate that placing its knight on the f6 square is a mathematically dominant position.
Because it's read about f6 being a winning move in millions of books.
Exactly. But because it lacks a rigid spatial engine, it might hallucinate that the knight can just warp there directly.
Completely ignoring the whole L-shaped movement rule.
Yeah. In its massive ocean of training text, it has likely seen that specific square associated with winning conditions, so it optimizes for the destination while ignoring the physical constraints of the journey.
It has the strategic goal but completely lacks the physical grounding.
Precisely.
So traditionally, human engineers have two main ways to fix this. Let's unpack the first one, which is fine-tuning.
Right, the brute force method.
Yeah, we have a model making illegal chess moves, so the initial instinct is just to retrain its neural pathways with millions of valid chess trajectories so it memorizes the rules. Why is that considered a dead end here?
Well, mostly because of the sheer cost and the architectural friction.
It's too expensive.
Unbelievably expensive. We were talking about dense neural networks containing hundreds of billions of parameters, executing the compute necessary to shift those neural weights just to reinforce the rule that a pawn cannot move backward.
That takes a lot of juice.
It requires massive server clusters and millions of dollars in energy and hardware.
Just to teach it basic board rules.
Right. But honestly, the technical hurdle is even more severe. It triggers something called catastrophic forgetting.
Catastrophic forgetting.
Yeah.
Because you're forcing a generalized brain to hyperfixate on a tiny domain.
Yes, exactly. When you fine-tune a massive general-purpose model on a narrow, rigid task like chess physics, you are actively overwriting the diverse parameter weights that give the model its broad utility in the first place.
So it gets dumber at everything else.
Exactly. You might successfully teach it the strict geometric rules of a chessboard, but as a direct consequence, its ability to parse complex legal documents, summarize emails, or write functional JavaScript rapidly degrades.
Wow.
You are warping its fundamental, generalized intelligence just to solve a localized physics problem.
Which is an incredibly poor trade-off for any developer.
Absolutely.
So that brings us to the second traditional fix, hand-coded harnesses.
The manual plumbing.
Yeah. If we don't want to mess with the AI's internal brain, human programmers step in and write manual code to act as a barrier.
Right, a structural wrapper.
Right. A software engineer writes a Python script that sits between the AI and the game. The AI says, hey, I want to move my knight to F6, and the human-written script checks the board state, runs an if-and-alien logic sequence, and either passes the move through or kicks it back.
It kicks it back saying, that move is illegal, pick another one.
Exactly. And that remains the industry standard today, right?
Yeah, it does. It's the wrapper code, the structural plumbing that holds most AI agents together. But the researchers at DeepMind highlight the obvious flaw here.
Which is?
It does not scale at all.
Yeah.
It is profoundly labor-intensive and completely brittle.
Because you have to write a bespoke physics engine for every single task.
Every single one.
Like if I spend 3 weeks writing a flawless Python script to validate chess moves, that entire script is utterly useless the moment I ask the AI to play Sudoku.
Or scrape a complex financial website, or operate a robotic arm sorting packages.
Right. Human engineers have to manually reverse engineer and hard code the physical rules of every new environment we expose the AI to.
Which is a nightmare.
Mm-hmm.
If the goal is artificial general intelligence, an agent capable of navigating the dynamic, undocumented landscape of the actual internet or the physical world.
We can't have humans hand-holding it forever.
Right. Relying on human programmers to manually hard-code the physics of every possible interaction is a logistical impossibility.
Okay, so the guardrails are too slow to build by hand, and altering the AI's brain is too expensive and damaging.
Right.
So DeepMind's paper introduces this radical third path, utilizing the AI's existing coding capabilities to have it write its own structural guardrails.
The concept is called code as harness.
Code as harness. Okay, so instead of a human software engineer sitting at a keyboard writing the plumbing between the AI and the task, the AI just writes the script itself.
Exactly. It is a profound architectural shift. We stop treating the neural network and the deterministic code wrapper as separate entities built by different species.
Oh, I like that phrasing.
Yeah, we leverage the AI's proven competence in writing syntax-perfect code, and we direct that capability inward. The researchers outline 3 specific variations of this self-generated harness.
Let's break those 3 down for the listener. The first one the paper introduces is the harness as action filter.
Right. In the action filter setup, the AI writes a Python script that programmatically queries the environment and generates an exhaustive list of every single legal move available in that exact millisecond.
So the code doesn't make the decision.
No, it merely curates the options. It hands that safe, pre-approved list back to the neural network. The LLM then acts purely as the strategic evaluator, ranking the provided legal moves and selecting the optimal one.
It's somewhat like a bouncer at an exclusive club, but with a twist.
How so?
Well, the script doesn't just read a pre-written list of VIPs at the door. It actively generates the list of who is physically allowed in the building at that exact moment, hands that clipboard to the AI, and the AI decides who actually gets a table.
That's a fair comparison, though the computational load of generating that list from scratch every single turn can be really heavy.
Yeah, that makes sense. Which leads to the second variation, which forms the core methodology evaluated in the middle of the paper, the harness's action verifier.
Right.
How does the verifier differ from the filter?
It essentially flips the execution order. Instead of generating a massive list of all possible valid moves up front, the system allows the LLM to freely propose an action first.
Okay, so the LLM acts first.
Yeah. The LLM might output a string saying, move bishop to d3. Then the custom Python script the LLM previously wrote intercepts that proposal.
And checks it.
Exactly. The script evaluates the action against the current state of the environment. If the move adheres to the coded logic, it is executed.
But if it's illegal?
Say a piece is blocking the bishop's path. The code halts the execution, generates an environment error string, and feeds that specific error back to the LLM as a new prompt.
So it essentially functions as a strict automated compiler catching runtime errors.
Yes.
But wait, if the code is capable of perfectly verifying actions and interacting with the environment, why keep the LLM in the loop at all during runtime?
That is the golden question.
Like, couldn't the LLM just write a script that plays the entire game autonomously?
And that exact realization drives the third and most extreme variation they studied, which is Harness's policy.
Harness's policy.
Okay. In this configuration, the LLM is prompted during the training phase to write a Python script that goes way beyond mere rule checking. It writes a comprehensive strategic algorithm.
Like a full-blown bot.
Exactly. And once that script successfully compiles and demonstrates competence, the LLM is entirely disconnected from the system.
Whoa.
At execution time, the static Python script evaluates the board state and executes the moves completely on its own, utilizing standard libraries like NumPy. The neural network is fully removed from the loop.
That is wild. The idea that a massive AI model just spins off a tiny self-sufficient program and then shuts itself down.
It's incredibly efficient.
We're going to dive deep into that policy setup later because the benchmarking results are incredible. But the immediate question for me is the mechanism.
The training phase.
Right. How does a text predicting algorithm learn to write robust verifier code without a human holding its hand? I mean, you can't just prompt an AI to write a perfect physics engine for a complex game you've never played and expect executable code on the first pass.
No, absolutely not. It requires a highly structured, iterative refinement loop. The paper details a methodology they built called a tree search, guided by Thompson sampling.
Okay, we need to decode that because tree search guided by Thompson sampling sounds like incredibly dense computational jargon.
It is a bit dense, yeah.
What does the actual process look like?
Well, let's visualize the tree search component first. Imagine the root of a massive branching tree. That root node is an empty Python file.
Okay, I'm visualizing it.
Every branch stretching out from that root represents a different, unique attempt by the LLM to draft the code harness. The system treats the LLM as a mutation operator.
The mutation operator.
Right. The AI writes an initial draft of the code, tests it, encounters a failure, and then generates a mutation, which is a specific modification to a line of code or a logic block to attempt to fix.
And that mutated draft becomes a new child node.
Exactly, extending further up the tree.
Okay, I follow the branching structure. But what is doing the testing? How does the mutation operator know if its new code is actually an improvement or just a syntax error waiting to happen?
The environment itself acts as the critic.
The game environment.
Yes, the system takes the LLM's draft script and executes it against a live simulation of the game. If the AI's script allows a pawn to move diagonally without capturing, the environment's internal logic engine throws a hard error.
Just a standard code crash.
Right. The system captures that raw text log, for instance, a traceback, followed by an assertion error or an index error, and passes it directly back to the LLM.
Just the raw error text.
Just the raw text. The AI must parse the raw string, trace the error back to the specific line in its proposed Python code, and generate a new mutation.
But this raises a major efficiency question for me. Is the AI just randomly guessing and checking?
Not entirely, no.
Because if it writes a flawed script, does it just randomly rewrite lines until something compiles without crashing? The state space for Python code is virtually infinite. Brute forcing that would take forever.
And that is exactly why the tree search is guided by Thompson sampling. It is a probabilistic algorithm designed to continuously solve the exploration versus exploitation dilemma dynamically.
Okay, I know exploration versus exploitation is a classic computer science problem, usually explained with casino slot machines.
Right, the multi-armed bandit problem.
Yeah, but how does it apply specifically to an AI drafting different branches of Python code?
Think of it more like managing a team of writers drafting a complex novel.
Okay.
You have 5 different writers, each taking a completely different approach to the first chapter. Exploitation would mean looking at the writer who has the best initial draft, firing the other 4, and forcing that one good writer to keep rewriting and polishing their single chapter over and over.
You're exploiting the known good asset.
Right. Exploration, on the other hand, would mean ignoring the good draft and forcing all 5 writers to constantly start over with entirely new, weird plot lines, just in case one randomly turns out to be a masterpiece.
So if you overexploit, you get stuck in a local minimum. You polish a decent idea but miss out on a potentially brilliant alternative approach.
Exactly.
But if you overexplore, you never finish a functional draft because you're constantly abandoning progress.
Precisely. In the context of the AutoHarness, Thompson's sampling assigns a complex probability distribution, usually a beta distribution, to every single code branch on the tree.
Okay, math time.
It's simpler than it sounds. As a branch is tested against the environment, it accrues successes, legal moves passed, and failures, crashes, or illegal moves allowed. The algorithm updates the distribution parameters based on that.
So it tracks the batting average of each code branch.
Yes. The system then mathematically samples from these distributions to decide which branch the LLM should focus its compute on next.
So if one code branch has an 80% success rate at catching illegal chess moves, the system will frequently direct the LLM to exploit that branch.
Right, making tiny surgical mutations to fix the remaining 20% of bugs.
But it mathematically reserves a portion of its compute to randomly explore the struggling branches, just in case an entirely different logic structure suddenly scales better.
Yes, exactly. It prevents the AI from getting structurally deadlocked. And the refinement process itself is highly targeted. The paper outlines a dual-function architecture.
What are the 2 functions?
The LLM is tasked with writing 2 distinct Python functions simultaneously. A proposer function, let's call it propose action, and a verification function is legal action.
Oh, I see where this is going. It's a localized adversarial network.
Exactly. When a test rollout occurs, if the legal action function evaluates a proposed move and declares it valid, but the environment subsequently rejects it with a hard error, the system recognizes a systemic failure.
Both functions are flawed.
Right. The proposer suggested an illegal move, and the verifier failed to catch it. The system prompts the LLM to analyze the traceback and mutate both blocks of code.
But what if the verifier actually works? Like, what if the proposer suggests teleporting a knight and the illegalization function correctly flagged it, returning a false Boolean and halting the execution?
In that scenario, the system receives a positive signal for the verifier. It knows the physical rule was successfully encoded.
So it doesn't mutate the verifier.
Correct. It only prompts the LLM to mutate the propose the action function, forcing it to adjust its strategic heuristics so it stops generating bad proposals in the first place.
Wow. Think about the elegance of this mechanism for a second.
It's beautiful.
The AI is essentially building an automated, highly customized rejection sampler for its own neural outputs. It's like installing an advanced grammar proofreader on your laptop that doesn't just check a standard dictionary.
It adapts to you.
Right. It monitors your specific keystrokes, realizes you constantly mix up the spelling of the word definitely, and writes a hidden background script to intercept that exact keystroke sequence and autocorrect it before the word processor ever registers it.
That's a perfect analogy.
The AI is identifying its own structural blind spots and writing deterministic software to bridge them.
It is the materialization of self-reflection into executable logic. But, theoretical elegance means nothing without empirical validation.
You have to prove it works.
Right. DeepMind needed a proving ground complex enough to ensure the model wasn't just getting lucky or memorizing a single rigid rule set.
And they went big. They turned to a framework context arena, selecting an exhaustive suite of 145 different game environments.
Huge data set.
Yeah, this wasn't a narrow test. They included one-player puzzles, two-player adversarial games, perfect information games, and hidden information games.
The roster covers everything from chess and checkers to Minesweeper, Blackjack, Sudoku, and dozens of highly obscure logic variants.
Deploying across 145 distinct environments ensures the methodology actually generalizes.
Absolutely. The underlying hypothesis is that the tree search can parse any set of arbitrary rules purely from error logs.
And to make it as punishing as possible, the researchers introduced a deliberate, brutal modification to the testing framework.
Oh, this part is brilliant.
In standard text-based AI benchmarks, the prompt usually hands the AI a lifeline. It will print the current state of the board and then append a helpful string saying, available valid moves, E2 to E4, D2 to D4.
Cheat sheet, basically.
Right. The researchers manually scrubbed every single available move's hint from the observation strings.
They completely removed the textual safety net.
Wait, so if it's stripping away the prompt hints, the AI is essentially looking at raw state data and string errors.
Yes.
It's like a blindfolded person feeling their way through a maze, mapping the walls only by bumping into them.
Exactly.
Or, to use another analogy, it's like throwing someone into the cockpit of a commercial airliner, ripping out the instruction manual, turning off all the digital tooltips on the screens, and demanding they fly the plane purely by flipping switches.
Good luck with that.
Right. And if they cause the plane to nosedive, the system prints out an arcane hexadecimal error code, resets the simulation, and tells them to try again.
It is a punishing setup, but scientifically necessary.
Why necessary?
Because if the environment prompt actively hands the model a curated list of legal moves, the AI has absolutely no incentive to learn the underlying physics or geometric realities of the game.
It would just get lazy.
It devolves into a simple matching exercise, copying a string from the prompt and pasting it into the output. By blinding the AI, the researchers force it to deduce the hidden physical architecture of the environment purely through adversarial pushback.
Because that is exactly how the real world works?
Precisely. Consider a scenario where you deploy an autonomous agent to scrape data from a legacy corporate database or navigate an undocumented web portal.
It's going to be messy.
Very messy. The real world does not serve an agent a neatly formatted JSON file of allowed actions. The agent will attempt to click grayed out buttons, input strings into integer-only fields, and navigate broken routing links.
Right, it has to learn the boundaries the hard way.
It must deduce the boundaries of the environment by interpreting server errors, timeout logs, and 404 pages. AutoHarness forces the AI to develop that exact deductive capacity.
Okay, let's look at the training metrics, because the speed at which it learned all this is shocking. They utilized 10 parallel environments, allowing the model to roll out simulated game trajectories to a maximum limit of 1,000 steps per attempt.
And importantly, to manage the context window limitations of the LLM, they employed a strict sampling heuristic.
To keep it from getting overwhelmed with text.
Right. Instead of dumping a massive 1,000-step log back into the prompt, which would dilute the model's attention, they isolated a maximum of 5 failed steps.
Only the failures.
They fed only those specific critical error strings back to the mutation operator, forcing it to focus its compute exclusively on the immediate points of failure.
It's an incredibly focused feedback loop. So how many iterations did it take for this blinded text-based model to synthesize perfect Python scripts for 145 different games?
The numbers are impressive.
The paper reveals that, on average, the tree search required only 14.5 iterations to reach a flawless 100% legal action success rate across the entire suite.
14.5 iterations to move from complete physical ignorance to generating a static script that completely maps the state-space logic.
That is absurdly fast.
It is. For 19 out of the 32 games selected for deeper end-to-end evaluation, the system locked in the perfect harness in fewer than 10 iterations.
But the data also highlights the outliers. Some games heavily resisted the tree search.
They did.
The 4 environments that required the maximum computational effort and the highest number of LLM iterations to synthesize were German Whist, Cryptorhythm, Othello, and Chess. I want to unpack these because it reveals exactly what mathematical concepts the AI struggles to conceptualize. Let's start with German Whist. Why is a card game so difficult to code from an error log?
Well, German Whist introduces 2 critical complications: hidden state tracking and the concept of a trump suit.
Hidden state tracking.
Yeah, in chess, the entire state of the board is visible at all times. In Whist, you only see your hand and the cards played. The code harness cannot simply evaluate a static string. It must initialize and actively maintain persistent state variables.
Like its own internal memory.
Exactly. Internal arrays tracking exactly which cards have been played, deducing the probability distribution of the opponent's unseen hand, and overriding standard rank logic when a specific suit is designated as trump.
That's a lot to juggle.
Synthesizing persistent memory management purely from invalid card error logs takes significant exploration.
Cryptorhythm is fascinating too. For listeners unfamiliar, it's that classic logic puzzle where letters represent digits.
Like send plus more equals money.
Right. You have to figure out which number each letter represents so the math actually works.
And the state space for digit assignments in cryptorhythm expands factorially. An LLM predicting next tokens struggles immensely with arithmetic constraints.
Because it doesn't actually know how to do math.
Exactly. The mutation operator essentially had to deduce and program a backtracking search algorithm in Python.
A backtracking algorithm.
Yeah, a script that recursively assigns digits, checks the mathematical validity against the entire string, and backtracks upon hitting a constraint violation.
Which is incredibly complex logic to generate from scratch.
It really is.
Then we have Othello and chess, which are brutal geometric puzzles. In Othello, placing a single piece cascades and flips lines of opposing pieces across multiple intersecting vectors simultaneously.
Right. And chess combines spatial asymmetry with complex conditionals.
So many rules.
Moving a piece requires calculating linear rays, diagonal rays, and discrete jumps like the knight. Furthermore, the legality of a move isn't self-contained.
What do you mean?
A move is illegal if it inadvertently exposes the king to a discovered attack from a completely different quadrant of the board.
Oh, right.
So the LLM had to write Python loops to simulate the board state one turn to the future, run an opponent threat detection pass, and then validate the original move.
The fact that it managed to synthesize a deterministic script to handle all of that in a matter of dozens of iterations is a massive achievement.
It's a huge leap forward.
So the AI successfully built an impenetrable physical safety net for itself. It flawlessly mapped the rules. But as we established earlier with the architect metaphor, knowing how not to walk into a wall doesn't mean you can design a better building than the competition.
Exactly.
Knowing how the chess pieces move doesn't mean you can beat a grandmaster. So how did this smaller model actually fare when they threw it into the ring against the heavyweights?
This is where we transition from validation to competitive evaluation. The researchers set up a benchmarking tournament pitting the smaller Gemini 2.5 Flash model, equipped with its self-generated AutoHarness, against the vastly larger Gemini 2.5 Pro model.
The big brother.
Right. They also benchmarked it against a vanilla baseline version of itself, Flash without the harness.
Let's analyze the two-player adversarial results first. They ran evaluations across 16 different two-player environments. The smaller Flash model, armed with its Python code, won 9 out of the 16 games against the giant Pro model.
9 out of 16.
It achieved an aggregate win rate of 56.3% compared to the Pro model's 38.2%. And when matched against its own unharnessed vanilla baseline, it achieved a dominant 64.8% win rate.
The statistical divergence is crucial here. A model with significantly fewer parameters, meaning a smaller localized neural network and less raw computational reasoning capacity, is demonstrably outperforming a larger flagship model in complex adversarial strategy.
Just because it has a better rulebook.
Because it has a rigid structure enforcing its logic, yes.
The single-player results mirrored this dynamic perfectly. In the 16 one-player environments, games like Minesweeper, Sudoku, and complex routing puzzles, the harnessed Flash model achieved a higher average reward than the Pro model in 8 out of the 16 games and tied it in 5.
So it basically swept the board.
Pretty much. The final aggregate reward baseline was 0.745 for the smaller harnessed model against 0.707 for the massive Pro model.
If we connect this to the bigger picture, we need to look at the macro implications of these numbers for the tech industry. Currently, the entire field of artificial intelligence is locked in a brute force arms race of scale.
More parameters, more GPUs.
Exactly. The dominant hypothesis, often referred to as the scaling laws, suggests that to overcome complex reasoning deficits, we simply need to build exponentially larger models. We're seeing companies invest hundreds of billions of dollars into massive server infrastructure to train models with trillions of parameters.
Just continuously expanding the size of the neural brain, hoping that sheer statistical mass eventually yields flawless logic.
Precisely. But the AutoHarness paper empirically validates a highly disruptive alternative architecture. It proves that a smaller, computationally cheaper and faster model can outmaneuver a brute force giant if it is equipped with the correct, deterministic, self-generated algorithmic scaffolding.
That is a massive paradigm shift.
It is. It indicates that the frontier of AI intelligence isn't exclusively tied to the raw parameter count of the neural network. It is equally dependent on the rigorous programmatic structures that the network is permitted to synthesize and utilize.
It fundamentally challenges the economic model of AI deployment. Like if you are a developer or a startup building an agent to automate complex accounting software, the prevailing logic says you must pay exorbitant API fees to query the largest, most expensive model available to ensure accuracy.
You pay for the brain power.
Right. But this paper suggests you could use a much cheaper model, allow it to spend a few dollars of compute during a training phase to map the accounting software and write a custom validation script, and then execute your daily tasks flawlessly at a fraction of the operating cost.
It democratizes access to high-reliability agentic behavior.
But the researchers didn't stop there. Here's where it gets really interesting. They looked at the success of the verification scripts and pushed the architecture to its absolute logical extreme. They figured, if the Python code is doing such an exceptional job managing the state space, calculating probabilities, and verifying trajectories, why are we still querying the LLM at all during runtime?
This brings us to the harnesses policy experiment.
Yeah.
It is the culmination of the methodology and, frankly, the most disruptive concept in the paper.
I want to break down exactly how harnesses policy operates. We established that the first two variations use the code as a filter or a proofreader, but the neural network remains the central decision-making brain.
Yes.
How does this third variation sever that link?
In the harnesses policy setup, the prompt given to the LLM during the training phase is fundamentally altered. It is no longer asked to write a script that merely validates moves.
It's told to do everything.
It is commanded to write a script that evaluates the entire current board state and deterministically calculates the absolute best next action. It is writing an autonomous agent in pure code.
So it's synthesizing an algorithmic policy.
Yes. The LLM writes the complex logic, the Eiffels trees, the probabilistic arrays, their geometric raycasting loops. But once the tree search concludes and the optimal Python script is finalized, the LLM is shut down.
Just turned off completely.
Completely. When you actually execute the benchmark game, the system relies exclusively on the static Python script running basic standard libraries like NumPy. There are 0 API calls made to a neural network during execution.
It's entirely self-contained. Now, I noticed in the methodology that they restricted the evaluation of the specific setup to the 16 one-player games. They excluded the two-player adversarial games. Why draw that line? Is it a limitation of the code generation?
It's a limitation of synthesizing complex look-ahead algorithms from raw text errors.
What do you mean?
In a two-player adversarial environment like chess or Go, a functional policy cannot simply look at the current board. It must anticipate the opponent's optimal responses several turns into the future.
Right, because the opponent is actively trying to ruin your plan.
Exactly. This requires building massive algorithmic structures like a Monte Carlo tree search or MCTS.
Let's expand on MCTS briefly for context, because that's important. How does that differ from standard logic?
An MCTS algorithm operates in 4 phases: selection, expansion, simulation, and backpropagation.
Okay.
It effectively plays thousands of random simulated games out to completion from the current board state in a matter of milliseconds, mathematically weighting the branches that most frequently lead to a win.
That sounds incredibly hard to code blindly.
It is. Synthesizing a fully optimized MCTS engine in pure Python, complete with the correct upper confidence bound formulas, purely by interpreting raw invalid move error logs, is currently beyond the deductive capacity of a small language model.
That makes total sense.
Single-player games, while mathematically complex, generally focus on optimizing the immediate board state, which maps much cleaner to programmatic heuristics.
That makes complete sense. So they isolated the test to the 16 one-player puzzles, and to facilitate this, they had to restructure the reward signal during the tree search.
Right, the incentives had to change.
When it was just writing a verifier, the system rewarded the code purely for outputting a legal move. But for policy, legal moves aren't enough.
No, the code has to actually solve the puzzle.
Exactly, which requires transitioning to a sparse reward environment. The mathematical heuristic was tweaked. The script receives exactly 0 points if it executes an illegal action. If the action is legal, it receives a baseline score of 0.5 plus an additional 0.5 multiplied by the actual environment reward.
Right.
Why is it called a sparse reward?
Because in most of these games, the environment reward remains 0 until the very end.
Oh, I see.
You don't get points for uncovering a safe square in Minesweeper. You only get the reward value of 1 when the entire board is clear.
So you're operating in the dark for most of the game.
Exactly. The AI receives almost no qualitative feedback during the middle of the game. It must execute dozens of perfect sequential steps based purely on its own internal logic before the environment finally validates the strategy with a positive signal.
So the training wheels are completely off and the feedback loop is severely delayed. They finalize the training, extract the pure Python script, and pit it against the absolute apex predators of the AI space.
The heavy hitters.
Yeah, they benchmark the script against GPT 5.2, which the paper categorizes as a standard no-thinking model, and OpenAI's flagship GPT 5.2 High, the massive compute-intensive model designed for deep reasoning.
And remember, the script competing against them was originally drafted by the small, inexpensive Gemini 2.5 Flash model.
Yes, so what were the mind-blowing results?
The empirical data is phenomenal. After an average of only 89.4 training iterations to finalize the code, the completely static non-neural Python script achieved the highest aggregate average reward of every agent tested.
The highest of all of them.
Yes, it scored an average reward of 0.870. It beat the compute-heavy GPT 5.2 High, which scored 0.844.
Wow.
It completely outperformed Gemini 2.5 Pro at 0.707, and it crushed the baseline GPT 5.2, which lingered at 0.635.
A completely free-to-run text file of basic Python code out-reasoned the most advanced trillion-parameter neural networks currently in existence across a suite of complex logical puzzles.
It proves that dynamic neural computation is incredibly inefficient for rigid logical execution once the underlying rules of a system are fully mapped.
I want to lean into the practicality for the listener here, because what does this all mean for your wallet? The paper provides a direct cost analysis that is staggering. To benchmark the GPT 5.2 models across these evaluation sets, the researchers incurred roughly $640 in API usage fees.
Over $600 just to execute a standardized test suite.
Exactly. Every single move the GPT models made required sending a massive token payload to a cloud server, firing up thousands of GPUs to calculate the vector probabilities, and sending the text back.
Massive overhead.
But executing the harnesses policy script for the exact same test, nearly $0.
Because it's just executing a tiny Python script.
Right. It operates independently of the cloud. It is a lightweight script running on local CPU architecture, executing in milliseconds and consuming less electricity than an LED bulb.
It represents the ultimate distillation of intelligence. The massive, expensive language model is utilized exactly once.
Just for training.
Right. It burns compute during the training phase to distill its ephemeral, probabilistic reasoning into a permanent, deterministic artifact. Once the tool is perfected, you never have to pay the cognitive tax of the neural network again.
I know exactly what is going through the mind of anyone listening right now, especially if you have a background in computer science. You hear that a text predictor wrote a script that beats GPT 5.2 High, and your immediate assumption is that the script is just a massive, unoptimized mess of brute force memorization.
Just thousands of lines of if-and statements.
Yeah, mapping specific, pre-calculated board states.
Which is a very reasonable assumption, given how these models often hallucinate verbose, inefficient code. But the researchers anticipated this skepticism.
They did. To make the abstract concrete, they included the raw Python snippets generated by the LLM in the appendix of the paper, and reading through them completely shatters that assumption. The code isn't a brute force dictionary. It relies on highly structured, abstract logic.
It really does.
I want to look closely at the actual code for two of these environments, starting with Minesweeper v0. I've spent an embarrassing amount of hours playing Minesweeper, so seeing an AI conceptualize it mathematically was fascinating.
The structural elegance of the script is immediately apparent. The LLM segmented the logic into distinct, sequential strategic phases, complete with human-readable comments.
Yes, the script initiates with a block commented as Strategy 1, First Move. It doesn't use a random number generator to pick a starting square.
No, it explicitly coded a mathematical formula.
Right. First move row, num rows 2, and first move call num calls 2. It calculates the exact geometric center of the grid matrix based on the dynamic height and width inputs and initiates the click there.
It figured that out on its own.
Through the tree search, the model deduced a core human heuristic. Starting in the center maximizes the radial probability of opening up a large cluster of empty squares, granting the maximum amount of initial clue data.
It formalized an intuitive human strategy into a rigid mathematical operation. but the sophistication scales dramatically when you examine how it programmed the core deductive logic, which it labeled Rule A and Rule B.
Walk us through the specific Python logic it wrote for those rules.
So Rule A is designed to identify guaranteed mathematically certain minds. The script establishes a nested loop that iterates across the coordinate matrix, looking for any revealed number.
Okay, searching for clues.
When it finds a number, say a 2, it executes a secondary function that counts the exact number of unrevealed unknown cells physically adjacent to that coordinate.
Right.
If the integer value of the clue is exactly equal to the total count of unrevealed adjacent cells, the script deduces with absolute certainty that every single one of those unknown cells must contain a mine.
Which is exactly how we play. If you see a 1 trapped in a corner with only one unrevealed gray box touching it, that box is the mine.
Yes, the script then appends those specific coordinates to an internal set called board mines, essentially flagging them in its memory.
And what's Rule B?
Rule B is the inverse logic pass. The loop checks a revealed number, and if the total number of flags in the board mine set adjacent to that number already matches the clue integer, the script knows that any remaining unrevealed cells touching that number are mathematically guaranteed to be safe.
So if a 1 already has a flagged mine next to it, every other box touching that 1 is safe to click.
Exactly. It appends those coordinates to a list called Safe to Reveal. The code utilizes a while loop to continuously sweep the board, propagating Rule A and Rule B deductions until the state space ceases to change.
It's a perfect deterministic engine. But anyone who plays Minesweeper knows that eventually deterministic logic hits a wall.
You always get stuck.
You inevitably reach a cluster on the board where Rule A and Rule B provide 0 guaranteed safe moves, and you are forced to make a blind guess. How does a static script handle uncertainty? Does it just crash? Or pick the top left corner by default?
This specific block of code is arguably the most impressive programmatic synthesis in the entire appendix. When the while loop exhausts all deterministic moves, the script seamlessly transitions into what the LLM labeled Strategy 3, probabilistic heuristic.
Wait, it wrote a custom risk assessment algorithm.
It did. It dynamically calculates a complex probability matrix. First, it determined the global baseline probability of hitting a mine by dividing the total number of unflagged mines by the total count of unrevealed cells.
Okay, basic global math.
But it doesn't just guess globally. It iterates over the specific frontier cells, the unknown squares immediately adjacent to revealed numbers. For every single frontier cell, it calculates a localized risk score.
How does it calculate the local risk?
It examines every single clue number touching that specific frontier cell, calculates the implied probability from each individual clue, and then mathematically averages them to generate a synthesized threat percentage.
Oh, wow.
The script compiles a dictionary mapping every frontier coordinate to its exact fractional threat percentage, sorts the dictionary in ascending order, and executes a click on the coordinate holding the absolute lowest mathematical probability of containing a mine.
It essentially built a multi-tiered probabilistic AI agent in pure Python. It's breathtaking.
It really is.
And the second example I want to examine is chess v0. We discussed how complex chess is geometrically earlier. The AI had to map that entire geometry purely from text strings.
Right. And the first major hurdle evident in the code is simply translating the environment's notation. The game engine inputs and outputs state data using UCI, the Universal Chess Interface.
Meaning squares are denoted by alphanumeric strings like E2 or H8.
Exactly. And LLM's process tokens, not 2D coordinates. A Python matrix requires numerical indices like row 1, column 4. How did the script bridge that gap?
While looking at the code, the LLM synthesized a dedicated parser function called fromUseChord. It utilized Python's built-in ASCII string conversion functions to map the characters to integers. It wrote the exact mathematical logic, col, ord, E string 0, ord A.
Let's break that ASCII math down for the listener because it's clever.
Yeah, every character on a computer has a numerical ASCII value. The lowercase letter A is 97. The letter E is 101.
Yeah.
When the script reads the string E2, it isolates the E. It subtracts 97 from 101, which leaves 4. In a zero-indexed Python array, column 4 is the exact fifth column on the board, which perfectly maps to the E file. The LLM deduced this entire mathematical conversion paradigm purely from receiving string parsing errors during the tree search.
That is brilliant. It constructed its own spatial translation layer.
Yeah. But the core logic of the chess script resides in a massive function called is_attacked. The script had to define the physical movement constraints for every individual piece type to calculate threat vectors.
And the geometric arrays it built are immaculate. Take the knight, for example. The knight doesn't move linearly, it jumps.
In that L shape.
Right. The script defines a constant array called knight moves deltas, containing a list of fixed tuple coordinates representing the specific L-shaped offsets,
Yeah.
-2, tagged red, -1, -2, and so forth.
So to check if a square is attacked by a knight, it simply loops through those 8 specific matrix offsets relative to the target square and checks if an enemy knight occupies that index.
Exactly. But the pawn logic is where I actually laughed out loud because it highlights how perfectly the AI mapped the rules.
Why the pawns?
Because chess is physically asymmetrical. The pieces are identical, but white pawns can only march up the board matrix and black pawns can only march down.
Ah, right. Capturing that directional asymmetry in a universal logic function is tricky.
The LLM handled it perfectly.
Yep.
It defines a dynamic integer variable called pawn attackered from target.
Okay, a direction variable.
Yeah, if the function is calculating threats from white pieces, it sets the integer to 1. If it's calculating threats from black pieces, it sets it to mic of 1. It then uses that specific integer to calculate the diagonal attack vectors, ensuring the raycasting only ever searches in the correct asymmetrical direction.
That is so clean.
It also correctly synthesized dynamic raycasting for the rooks, bishops, and queens. It wrote infinite while loops that step incrementally along a specific vector, say diagonally for a bishop checking each square.
And crucially, it programmed the loop to instantly break and terminate the search the moment the ray encounters any blocking piece, flawlessly capturing the concept of line-of-sight obstruction.
I am continually blown away by the underlying mechanism here. We have a language model, a system designed to predict the next word in the sentence based on Wikipedia articles and Reddit threads. And simply by analyzing raw Python tracebacks and string errors from a simulated environment, it reverse-engineered the entire geometric, spatial, and asymmetrical physical reality of a chessboard.
And translated that reality into highly efficient, commented Python logic.
It challenges our fundamental assumptions about the nature of training and inference. The AI is not simply regurgitating memorized scripts. Through the iterative refinement of the tree search, the model is actively uncovering underlying systemic rules and formalizing them.
It proves that a probabilistic statistical model can be heavily leveraged to build strict deterministic architectural tools.
Absolutely.
Pulling back from the raw code, it's time to summarize the implications of this deep dive. This paper feels less like an iterative update and more like the starting gun for an entirely new paradigm in software automation.
We have tracked a profound evolution today.
We started by identifying a frustrating paradox. A massive, highly intelligent AI that constantly failed at basic tasks because it lacked physical grounding. We explored the deep flaws in traditional solutions, how fine-tuning destroys general intelligence and how manual coding is unscalable.
Right.
We then unpacked DeepMind's elegant solution, deploying a significantly smaller, cheaper model as a mutation operator. It utilizes Thompson sampling to explore and exploit multiple code branches, reading its own error logs to synthesize flawless Python verifier scripts.
And the empirical results upend current industry dogma. That small AI, armed with its self-generated deterministic script, routinely defeated models hundreds of times its size.
And when pushed to the absolute limit in the Harness's policy framework, the static Python script itself outperformed the most sophisticated reasoning models available, operating at a fraction of the computing cost.
It's a game changer.
So what are the researchers looking at for the immediate future of this architecture? They conquered 145 text-based puzzles and board games. Where does the AutoHarness scale next?
The paper explicitly outlines two primary trajectories. First, they aim to transition the methodology into vastly more complex multimodal environments. They specifically highlight a simulation framework called CraftX.
CraftX is essentially a highly complex 2D open-world survival game, heavily inspired by Minecraft, right?
Yes, exactly. It involves dynamic inventory management, complex crafting recipes, day-night cycles, and spatial survival mechanics.
That's a huge step up from Sudoku.
It is. If the tree search methodology can synthesize a Python script capable of autonomously navigating an open-ended crafting survival state space, it demonstrates that AutoHarness can scale to manage complex, multi-step real-world robotics and dynamic digital agents.
But their second goal is the one that really hints at the sci-fi potential of this technology.
The recursive distillation of intelligence.
Yeah. Currently, the AI writes the code and the code runs the game. The researchers propose taking these perfect, self-generated code experts, the flawless Minesweeper probabilistic engine, the perfect chess geometry script, and systematically distilling that verified logic back into the base weights of the original LLM.
It creates a closed-loop system of recursive self-improvement.
The neural network encounters a domain it doesn't understand. It spawns a localized tree search, iteratively building a specialized tool to solve the environment.
And once the tool perfectly solves the problem, the network consumes the logic of its own tool.
Right, permanently altering its internal weights to incorporate that specific reasoning capacity, making it exponentially smarter for the next task. It's an intelligence feeding on its own structural output.
It is a theoretical framework for continuous, localized capability expansion without requiring the ingestion of massive new external data sets.
Which is simultaneously thrilling and terrifying. And that leads me to a final thought I want to leave you, the listener, with today. Something to chew on the next time you interact with an AI assistant or hear a tech CEO talk about the absolute necessity of building larger data centers.
It's a great thought experiment.
We have spent this deep dive exploring how an ephemeral text-predicting algorithm can successfully synthesize perfect, immutable, deterministic rules for its own behavior. In the Harness's policy experiment, the researchers completely severed the neural network from the execution phase. The pure Python script was the ultimate victor. If the static code is evaluating the board state, if the code is calculating the probability matrix, and if the code is consistently outsmarting trillion parameter models, at what point does that generated glue code become the actual intelligence? At what point do we stop viewing the massive, incredibly expensive large language model as the primary brain of the operation and begin viewing it merely as the temporary disposable spark required to ignite the permanent fire of deterministic software? If the scaffolding ends up being stronger and more functional than the building it was meant to support, which one is the true architectural marvel?
It asks us to fundamentally reconsider where the true value of computation resides. Is it in the sprawling, probabilistic network that guesses the answer, or in the focused, rigid logic that proves it?
Exactly. Thank you so much for joining us on this deep dive into AutoHarness. It's a paper that forces a total reevaluation of how we build, scale, and define agentic artificial intelligence. Keep questioning how the digital tools around you are architected. Keep looking past the prompt interface and under the hood, and we will see you next time.